All right, welcome back, statisticians. We are done with Chapter 6. We're moving on to Chapter 7, and that PDF is posted in Schoology. However, we are going to be kind of doing some of our own things as well. So you should have your notebook out. We'll kind of be taking some notes as we go. We're not really focusing on the book right now, but we will be using it pretty soon. So before we get started on the notes, this is where I would kind of present you guys a little offer here, and I would tell you that that I'm thinking of a number. Right? I'm going to pick a number between 1 and 10, and it's inclusive, so including 1 and 10. So I'm going to pick a number between 1 and 10, and if you guess it right, I would literally pay you $100. Okay? So now you're going to probably be thinking, okay, so what's the probabilities here? You know, what percent chance do I have to win this $100? And then I would offer, I'd let a student guess a number. So let's say I say, in fact I've typed the number into the calculator. It's on the home screen. So right now the graph is shown right there. The graph is shown right there. So as soon as I go back to the home screen, it's going to show us the number. So there's no cheating here. So I give the student an option to guess the number. Let's say they guess 7, right? And I tell them, no, unfortunately, you're wrong. You're not going to win this $100. But then I do something else. I say, well, I'm not going to change the number now. I'm going to keep the number the same number that's written in the calculator over there. And then I'm going to go to the next student, right? Well, the next student's not going to guess 7. They're going to guess something else. And maybe the probability gets better as we go, right? I say, no, the next student's wrong, the next student's wrong. Maybe we get all the way down to the 10th student. And the 10th student's thinking, oh, nobody else has gotten this, so process of elimination, I'm going to win the $100. They guess the final remaining number. And I tell them, no, sorry, you didn't win the $100. So now we're thinking, well, what's going on here? Well, then I remind you that we just finished a unit called discrete probability distributions. And now we're in a new unit called continuous probability distributions. And so the number that I was actually thinking of was 2.651152214, of course. And unfortunately, nobody guessed that number. So you're out of luck, you didn't win the $100. This is the idea of continuous versus discrete, right? I told you I was going to pick a number between 1 and 10. I did. This is a number between 1 and 10. It's just that the possible values were not discrete. It wasn't just 1, 2, 3, 4, 5, 6, and so on. It was all possible values between 1 and 10. And so that's what we're going to be talking about. So first of all, the first type of continuous probability distribution we're going to talk about is called the uniform distribution. So we are going to be talking about 7.1, and this is the uniform distribution. So a uniform distribution is pretty much what I started with that example. So in a uniform distribution, the probability, the uniform part of it means that the probability of every single outcome is the same, okay? So the probability of every outcome is the same. Every outcome is the same. So the probability of every outcome is the same. So for example, a number 1 through 10, I could show that graphically by saying, okay, here's 1, and here's 10. And the uniform piece about that is the probability of a 1 is the same as the probability of any other number, which is the same probability as any other number. And we get this sort of straight line going down. And essentially what this creates is a rectangle. Okay? So here's the interesting thing. Why was I so confident that nobody would be able to guess this 2.65115.214? Well, this is where we get sort of like an interesting mathematical thing that happens. The probability of, if I were to truly randomly select a number, the probability of you guessing what that number is essentially zero, right? Because based on probability, we take the number of outcomes. So the number of times this number occurs between 1 through 10 is only once. And then we divide it by the total possible outcomes. Well, how many numbers exist between 1 through 10? Including all irrational, rational numbers. Well, that's an infinite number of possibilities. So we're essentially taking 1 and dividing it by infinity, which turns out to be essentially 0. So the probability of an individual value in a continuous distribution is essentially 0. So what we do in statistics is we don't look for the probability of one individual number. We look for the probability of an interval, right? Like a range of numbers. If I were to represent that situation and say, you don't have to guess a number, you can guess between two numbers. So you could say, oh, I think the number is between 2 and 3, right? Then you would be correct, right? So that's the idea with continuous probability. So what we do here is this is essentially a probability density function. Probability density function. Okay, and that might seem interesting here. The PDF is something we have seen before, right? And I'm not just talking about computer PDF files. No, I'm talking about the probability density function, the thing that we've been using in our calculator. So that's PDF. CDF, the other option we've been using in our calculator, cumulative density function. So it's adding everything less than, right? So for this uniform distribution, in fact, in all continuous distributions, all continuous probability distributions, that's a B. In all continuous probability distributions, the area under the curve represents the probability. So that means in this uniform distribution, the area represents the probability. Because this is a probability distribution, that means that the area, the total area, must equal, what's that probability distribution to be a valid probability distribution? It has to total 1, right? The total area has to be 1, or 100%, right? So with uniform distribution, it's kind of easy to find probabilities because we're talking about a rectangle. And when we're finding areas of rectangles, we know that's just length times width. So for example, back to this, picking a number through 1 through 10, we see that we know the length, right? The length of this rectangle is 9, actually. So because we have a length of 9 here, because I didn't say 0 through 10, whatever, the idea is that we're going to multiply this length by this width, and it has to equal 1. Essentially, what we're going to figure out is that we don't know what the height is yet, but we figure that out based off the length and based off this idea that it equals 1. So because this is a length of 9, the height of this, we're just going to do the reciprocal or do 1 over the length. And so this would be 1 over 9. Now we can make sure that that's correct, because what's the area of this rectangle? Well, this is a length of 9 times 1/9 width. 9 times 1/9 is 1, right? That's the total area. Okay, so how we would be using this then would be to say, okay, so what's the probability? What's the probability that the number was between, let's say, 2 and 5? So I could say between 2 and 5, or we can use the probability notation and say the probability of x being between 2 and 5, right? 2 is less than x is less than 5. These two things are essentially the same. So what would that probability be? Well, we would just find the area. So if I'm talking about this probability now, what I'm going to do is, let's do this. Here's 2. Here's 5. And so what we're doing is we're essentially finding this area now. How do we find that area? Well, what's the length? The length would be 3 times, what's the width? 1/9. Right, and so we get the probability of that to be 1/3, or essentially 33.3%. Okay, so the probability that the number was between 2 and 5 is essentially 33.3%. Okay, and so that's the uniform distribution. So I suggest drawing it just because I think visually it's easy to see it. That would be my suggestion to you. So for example, let's try for example, what's the we have a uniform distribution. So remember, we got to know that it's a uniform distribution first. From, let's say, 24 to 38, find the probability of the variable taking on a value, let's say, between 27 and 30. Okay, so how are we going to do this? Well, like I said, the first thing I would do is I would try to draw this. So I'm going to just kind of make my axes, and I'm just going to put in some labels here. There's 24, there's 38. Okay, I'm not really concerned about the scale here. I just want to sketch this out. There's 24, there's 38. Here's my density function. Okay, so now I got to figure out what this height is. Well, my current length is, what's 38 minus 24? It'd be 14. So 1 over 14 is the height of this uniform distribution. Okay, so now 27 to 30, well, I'm going to find that, where that would be, maybe right there. So I'm finding this area. The distance, the length of that rectangle would be 3. So the probability of 27 to 30 is equal to 3 times 1 over 14. So that's 3 divided by 14. So let's see what that comes out to be. 3 divided by 14 is about 21.4%. 21.4%. Okay? So, a couple interesting things with continuous probability distributions. Number one, the probability of any individual value is 0. However, you start adding up all of those probabilities and somehow you get 100%. Kind of some weird things going on there, but that's just the way that the math works. So, uniform distribution, all we're doing is we're finding the area of a rectangle. This idea that we talked about, the area being the area being the probability, so that's one of the main takeaways of this section, okay? The area is equal to the probability. That's going to be really important to remember moving forward, and so on, okay? So that's pretty much it for uniform distribution on this first section. And then we're going to kind of extend this to different shapes and talk a little bit more about more different continuous distributions. All right, I will see you next time.